Good morning to all. Welcome to the channel Firjan. Today we discuss electric charges and electric field lesson. Electric field due to plain sheet of charge and thin sheet. Plain sheet na single layer. So this is the plain sheet. This is the plain sheet of charge. In this one, charge is distributed uniformly. It is infinite length. Infinite length. For example, how why we are saying this infinite length na? For example, this is the board. In this one, this dot is very small na. So its board is infinite comparing with this one. Like that here also, this is plain sheet which is infinite. Here from this plain sheet, x distance. This x is very small compared to dimensions of the plane sheet. At x distance, what is the electric field? So that we find out. For that, at x distance p point, we draw the Gaussian surface. For this plane sheet, what is the Gaussian surface now? Cylinder is the Gaussian surface. Cylinder is the Gaussian surface. This plane sheet have charge is there. Infinite sheet this one. So that charge, how to find out now? See, for calculating charge, we use the new term. So that is surface charge density. Surface charge density. What is surface charge density means? Charge per unit area. Charge per unit area is called surface charge density. That we can write sigma equal to Q by A. So this is what is the use now here. See, 1 meter square. How much charge is there? For finding that, we can use surface charge density. For example, 2 meter square area. How much charge is there? 2 sigma. 3 meter square area. What is charge? 3 sigma. It is infinite sheet na. So that's why we can use sigma. Yes na. Since by using this surface charge density, we can calculate the what is the charge in this plane sheet. See, before that, here we can select Gaussian surface. Why we are selecting Gaussian surface now here? For finding electric field due to this plane sheet. What is the electric field? For that, we can select Gaussian surface or Gauss law we can use and find the electric field for this infinite plane sheet or infinite long wire. This type of we can use. We can find electric field by using Gauss law. So what is Gauss law now? Net electric flux through a closed surface is 1 by epsilon naught times net charge enclosed by the surface, means pi closed equal to q inside by epsilon naught. This is the Gauss law. Here see, by using Gauss law, here we can select Gaussian surface. What is the Gaussian surface now? Here cylinder is the Gaussian surface. What is the use of this one now? This Gaussian surface should be symmetric about charge or charge distribution. Symmetric means equal. So all direction charge will be distributed equally. That is, see, in this Gaussian surface, this is the Gaussian surface now. Every point, this point, this point, or this point, or this point, this Gaussian surface, electric field is same, constant, or equal at every point on the Gaussian surface. See, this in this Gaussian surface, theta. Theta means angle between the electric field and the area vector. For example, see, this is the positive charge. Positive charge na electric field is radially outwards. See, this is the electric field. This is the direction of electric field. See, this is the direction of electric field. In this one also, see, radially outwards. This is the electric field direction. See, this electric field is what now here in this surface, Gaussian surface, this point, this point, this point, every point same, equal, constant. In the same way here, see, in this Gaussian surface, theta means it is the electric field na. Its area vector, see, we can select here this point. This area vector is this one. See, dA is the area vector. See, area vector is always means area vector and electric field, between these two some angle is there, that theta is always same at every point on the Gaussian surface, means theta is same at every point on the Gaussian surface, either it is 0 or 90. For example, this surface, see here, it is the point we can select area dA. This is outward normal and electric field is this one. See, both are in same direction. So what is the angle here? Theta 0. For example, here we can take, this is the area vector dA. We can select small area. This area vector is outwards normal. See, this is the electric field. See, angle what now here sees 90 degrees. See, what is the angle here? theta equal to 90. Here theta equal to 0. We can take this side, see here, this point we can select, it is the area vector dA, and electric field also same direction. See electric field. What is the angle now here? Theta equal to 0. Means theta is the angle between electric field vector and area vector. It is same, symmetric every point on the Gaussian surface. On a Gaussian surface, every point theta is same. Either it is 0 or 90. Either it is 0 or 90. So this Gaussian surface used to find the what is the electric field due to this plane sheet. See in this one, we have two surface, three surfaces is there. This is the first surface we can take. This is the second surface we can take. This is the third surface. See three surfaces. What is the flux through these surfaces? See here, flux through closed surface equal to q inside by epsilon naught. Here see flux through closed surface equal to pi 1 plus pi 2 plus pi 3. See here, this is the one, second, third surface. See theta is what here? 0. Electric field vector, area vector. Both are here, same direction. See this total area, this area of this surface is capital A. This area of this surface is capital A. Now see here pi 1. So means flux means integral E dot dA. E dot dA. E dot dA means, see here, E dot dA. Why not here? See this one, first surface, second surface, third surface. See pi 3. Here see E dot dA vector. E dot dA vector. E dot dA means integral E dA cos theta. Theta is what here? 0. Cos 0 here. Plus integral E dA cos 0. Here also see area vector and electric field vector both are in same direction. Theta equal to 0 plus E dA cos 90. Here see theta is 90. So why not area vector upward, electric field vector this direction. What is the theta is now here? 90. So this in this flux is 0. Why? Because cos 90 is 0. This 0. What we have here? So integral E dA E dA plus integral E dA we get. See now electric field is constant now, so write outside. So dA plus E integral dA. So means what we get here? EA plus EA. So means what we get here? 2 EA we get. What is the flux through closed surface now? This Gaussian surface now 2 EA. What here? Flux through closed surface equal to q inside by epsilon naught. Q inside by epsilon naught. See here flux through closed surface is what? 2 EA. I write here 2 EA is the flux through closed surface. Q inside by epsilon naught, that equal to q inside by epsilon naught. Q inside means this one. See here this area we can select this area. What is the flux through this one? See what is the charge in this one? What is the charge in this area? That's charge we find out. For that, what is the we can use? Sigma equal to q by a. Q means charge, a means area. Surface charge density equal to charge per unit area. From that, what we can write here? So q equal to sigma a. Sigma a. Say sigma means here surface charge density. Surface charge density. A means area. What is the q inside? Charge inside this surface now here. See here sigma a. Sigma a. Here we can write 2EA equal to sigma a by epsilon naught. This a cancel. What we get now here? E electric field equal to sigma by 2 epsilon naught. This is the electric field due to plane sheet, means single layer. So this is the electric field. See once again here electric field due to plane sheet. What we can first we discuss now? Surface charge density, charge per unit area. This is the plane sheet. In this one charge is distributed uniformly. So in this one x distance from the sheet at P point, what is the electric field? We find out. For that this x is also small and comparing with these dimensions. This x is very small comparing with the dimensions of the plane sheet. So in this one we can find out electric field point P. For that we can Draw the Gaussian surface. So draw Gaussian surface. From this has three surfaces there, 1, 2, 3. Here we find out electric field. What is the theta? Electric field theta here we find out. So electric field is always outwards. Here also electric field is outwards. Electric field is, this is the direction of electric field, area vector dA. What is the angle here? Theta 0. Here electric field is this direction, area vector is this one. So perpendicular, theta equal to 90. For second surface, electric field is this direction, area vector same. So theta equal to here 0. See total area na here A, total area na here A. What is the Gauss law? Means net flux through closed surface is q inside by epsilon naught. Net flux na here pi 1, here pi 2, here pi 3. Pi 1 na EDA, integral EDA, integral EDA, integral EDA. So EDA cos theta. Theta means here 0, here 0, and here is 90. So we can substitute cos 90 0. So EDA, EDA, 2 EDA, we can write E 2 EA. So that equal to q inside by epsilon naught. Q inside means here in this one, how much charge is there, that we find out. For that we can use surface charge density, sigma equal to q by A. So q equal to sigma A. What is the charge inside now? Sigma A. Sigma A, we can write here A cancel. So electric field equal to sigma by 2 epsilon naught. Means plane sheet, due to plane sheet, what is the electric field now here? Sigma by 2 epsilon naught. Smallest distance x, this condition is important. Small distance x from sheet, and comparing with the dimensions of sheet, it is very small. Comparing with the dimensions of sheet is very small. See, this is the electric field due to plane sheet of charge. Plane sheet of charge. Next, now we discuss electric field due to thin sheet of charge. Thin sheet we can take. See here, for that see a thin sheet now, this one. Thin sheet of charge. See, this is the thin sheet. In this thin sheet, it is a non-conductor. Non-conductor means not conducting material. It is non-conducting material. So non-conducting material na charge will be distributed whole. Totally charge is distributed. See this one. So plus charge is distributed in this one. See non-conducting. Before also we discussed conducting, hollow, conducting, non-conducting, conducting solid spheres or cylinders. This will be whatever conducting now. So charge will be resides on surface of the sphere. Non-conducting na charge will be whole. So total is there. So means inside whole is there, is distributed like this. So this is the means thin sheet. Due to this thin sheet, what is the electric field at all distance from the center, inside the sheet and outside the sheet, all distance. See for that here, see in this one, for example, this is the axis of this sheet. See all distance from this point here, P point, what is the electric field? So that we find out. For that what we can do now here, first see here, for this we can use volume charge density. Volume charge density. Volume charge density, why we are using like this? Not plain sheet, it is a thin sheet, means like this thickness is there. So it is volume, it volume charge density we can use. So what is now this one now? Rho equal to charge per unit volume. Charge per unit volume. Charge per unit volume. See, charge means Q, volume means V. So charge per unit volume means rho equal to Q by V. So means charge per unit volume is nothing but volume charge density. In this one we can use volume charge density. See for example here in this case, or distance from the center, what we can do now here, we can select Gaussian surface. We can draw the Gaussian surface. See, for this here Gaussian surface is cylinder. Here x distance, here also x distance. See, this is the Gaussian surface. So cylinder is the Gaussian surface for thin sheet. See, for example, here I draw. So this is the sheet, this is the sheet, this is the axis. From here, x distance from the axis, this point, what is the electric field? So that we find out. See, for that here we can draw the Gaussian surface. See, this side also same, x distance, we can draw the Gaussian surface. See, this is the Gaussian surface, cylinder is the Gaussian surface. In this one, charge is distributed, whole charge is distributed, whole part is distributed charge. See here, this is positive charge, positive charge. See, electric field lines radially outwards, this is the electric field lines. See here, it is the electric field lines. This side also same, see, this is the electric field lines. See here, in this Gaussian surface, what is the flux through Gaussian surface or closed surface, which is equal to q inside by epsilon naught. Means here we can use Gauss law and find the what is the electric field due to the thin sheet. For that, what we can write, use now Gauss law. So what is Gauss law? Flux through closed surface, flux through closed surface equal to q inside by epsilon naught, q inside by epsilon naught. See here, phi flux through closed surface equal to q inside by epsilon naught. Here flux through closed surface means we have three surfaces is there. This is the first surface, this is the second surface, this is the third surface. See here, it is the third surface, curved surface. See here, this is first surface, second, third surface. See, in these three surfaces, what is the flux passes through this one? That we find out. For that, what we can do now here, we can select small part. Here, area vector is this direction and the electric field is same. Both are in same direction. What is the angle now here? Theta equal to 0. So this one we can take now here. See, this is the area vector. We can select this area vector, and electric field also same direction. This is the electric field vector. So what is the angle between the here now theta and sorry, E and L area vector now? Theta equal to 0. Here see, we can select here small area, it is the area vector dA, it is the electric field. So both are here, see, 90 degrees, theta equal to 90 here. See, first surface theta is 0, second surface theta is 0, third surface theta 90. So flux through closed surface na, flux through closed surface equal to pi 1, pi 2 plus pi 3. Three surfaces is there. Flux through first surface pi 1, flux through second surface pi 2, flux through third surface pi 3. For example, see here, flux through closed surface equal to pi 1. So pi 1 means integral E dA cos theta here. See, second one, integral E dA cos theta. So third one also same, integral E dA cos theta. So what is the theta now here? See, first surface theta is 0. Here we can write 0. So theta is 0 here, second surface also 0. Third surface theta is 90. Here we can write 90. So means cos 90 0. That's why this term is 0. We have this only. See, phi closed equal to E dA, integral E dA plus E dA we get. See here, E outside we can write now, integral dA plus E integral dA we can write. So in this one we can write, see, EA plus EA. So we get 2EA. What is the flux through closed surface, Gaussian surface now here? 2EA. 2EA. See here, it is the actually thin sheet. In this thin sheet, what na, charge is distributed wholly, total part it will be distributed. Why? Because it is the non-conducting material. Non-conducting material charge will be totally distributed. For conducting material, charge will be on the surface. Means charge will be resides on the surface only. Inside is no charge. But non-conducting charge will be wholly, totally distributed. So like this one. See, in this one, what is the due to this thin sheet? What is the electric field? For that, what we can do now here? We use Gauss law. What is Gauss law na? Net electric flux through closed surface is equal to 1 by epsilon naught times charge inside the surface, inside the closed surface. So for that we can select Gaussian surface. So r distance from the axis p point, what is the electric field? So for that we can select the Gaussian surface. What is the Gaussian surface here? Cylinder is the Gaussian surface for this thin sheet. So what is the use of this Gaussian surface now? In Gaussian surface, charge will be distributed equally, and in the same way, see, means Gaussian surface should be symmetric about charge or charge distribution, and electric field on the Gaussian surface, every point is same, equal, constant. See, theta, angle between the electric field vector and area vector, this theta also same. This is the Gaussian surface now. In this one, see, theta equal to 0, here theta 90, here 0, means theta is the angle between electric field vector and area vector. This theta is at every point on the Gaussian surface is same. That means either it is 0 or 90. Theta is either it is 0 or 90. So these are the properties of Gaussian surface. In this Gaussian surface, we can use and find the electric field due to this one. See, for that what we can do, pi closed equal to q inside by epsilon naught. Here this surface, this are three surfaces. What pi closed equal to pi 1, pi 2, pi 3. What is the pi e dot dA? E dA cos theta. Cos theta means here 0. Why? Because this is the area vector, electric field vector. So that's why theta is 0. In the second surface, area vector and electric field vector both the same direction, 0. So third surface, see here, area vector this one, electric field vector this one, theta is 90. So it is 0. So this one, EDA, EDA. So means integral dA means EA, EA, what EA? 2 EA. So what is the flux through this Gaussian surface now? So means Gaussian surface, what is Gaussian cylinder? Cylindrical surface, what not? 2 EA. So means pi closed equal to q by epsilon naught, means pi closed is what? 2 EA, what here? Q inside by epsilon naught, q inside by epsilon naught. In this one, what is the charge is there? For that what we can use? Volume charge density, rho. Rho equal to q by v. Rho equal to q by v. What is rho here? So now charge now here q inside by volume. So volume means what here? Area. This area is capital A. This distance is here x, here x. Total is 2x. Volume means what here we can write? Rho equal to q by area into 2x. What we get here? Q equal to rho into A into 2x. This is the charge inside the Gaussian surface. What is the charge inside the Gaussian surface now? Rho A 2x means 2A rho x. 2A rho x. So means here we can write 2EA equal to q inside means rho A 2x by epsilon naught. This A cancel, 2 cancel. What we get now here? See, electric field is rho x by epsilon naught, means electric field due to thin sheet, due to thin sheet inside the thin sheet at all distance from the axis, x distance from the axis at point P. What is the electric field now? E equal to rho x by epsilon naught. See here, electric field is directly proportional to x, directly proportional to x. See here, for that what we can write now here? See, thin sheet now. See, this is x axis, it is y axis. Here electric field we can take, it is the thin sheet now. See, thin sheet. See, this is the thin sheet. In this thin sheet, so r distance less than capital R means inside the thin sheet at r distance means x distance. Here we can take x na, x is less than r. So x distance inside the thin sheet, what na here? See, directly proportional means it increases. So means here E proportional to x, E proportional to x. See, it increases. So that is the graph between electric field and x distance. Electric field and x distance. This is electric field is increases up to surface only. See here, from axis to surface, electric field from axis to surface increases E proportional to x. E proportional to x. Now we can take outside the surface. See here, for example, this one. Here we can take. So this is the, see, this is the thin sheet. See here we can take, this is the thin sheet. This is the thin sheet. In this one, it is the axis. From axis, x distance outside the surface at point P, what is the electric field, that we find out. For that, what we can take now, here also same Gaussian surface we can select. See here Gaussian surface, this is the Gaussian surface. So what is the Gaussian surface now? Here cylinder is the Gaussian surface for thin sheet. Cylinder is the Gaussian surface for thin sheet. This is the cylinder. See Gaussian cylindrical surface we can select for thin sheet, x or distance from or x distance from axis to outside point P. At point P, what is the electric field? See, it has positive charges. Now wholly is there, total part positive charges is there. Due to this positive charges, what now electric field is radially outwards. See, radially outward. Electric field is radially outward. For example, here we can select area. Area vector is dA. So means electric field is this one. So both are parallel to each other. So what is the angle now? Theta here 0. So in this one, electric field is this one E. C. Area vector we can select here this spot dA. So it is both are parallel. So what now here theta equal to 0. So means electric field vector and area vector both are in same direction. So theta equal to 0. Angle is the theta is the angle between electric field vector and area vector. This surface theta equal to 0, this surface theta equal to 0. This surface we can take here, area vector is dA, electric field is this one. See, so both are, what is the angle now here? Theta equal to 90. So means here also we have three surfaces is there. So for Gaussian cylindrical surface we can select from axis at x distance outside the thin sheet. For that, what is the electric field at this point? We find out. For that, we can select Gaussian cylindrical surface. So what Gauss law says? Flux through closed surface equal to Q inside. Here also same. What we can write now here? See, flux through closed surface, flux through closed surface. What here three surfaces is there? First one, it is the first one, it is the second one, it is the third one. Three surfaces is there. Three surfaces. Flux through three surfaces equal to what? Here now integral EdA cos 0 plus integral EdA cos 0 for this surface. So third surface is integral EdA cos 90. Third surface. Here at theta is 90. So this part is 0. See what we have, these two only. Flux through closed surface equal to E dA integral. See here E dA here. E is constant now, we write outside. So dA plus E integral dA we can write outside. So E A here plus E A here. What we get now? Flux through closed surface is 2EA is the flux through closed surface. 2EA is the flux through closed surface. Now see here, what is the Gauss law now here? Net flux through closed surface is Q inside by epsilon naught. Q inside by epsilon naught. See here, Q inside by epsilon naught. See in this case, Q inside. So this one, this part only, what is the flux through? Flux in, what is the charge in this surface? So for that, what we can use na? Volume charge density. Rho equal to Q by V. So from that, Q equal to what? Rho V. See here volume now, this part. So actually this thickness is small d. Thickness of the thin sheet is small d. Here see, x distance is there. Here no charge. Only this part is there. This is fixed. So means d distance. So volume now here, area in this one. Area, this area is A, and height, thickness is here d. So means height is d. So area into height na we get volume. So means what is the here volume na? Rho into volume is area into d. So means A into d. What is the charge inside the this Gaussian surface na? Here Q equal to rho A d we have. See here, actually what is the statement here? Pi closed equal to Q inside by epsilon naught. Pi closed means here what? 2EA. See here, 2EA equal to rho AD by epsilon naught. This AA cancel. What we get now? 2 2 E equal to rho d by epsilon naught E equal to so rho d by 2 epsilon naught. So here d is constant. So electric field is constant. Electric field is constant at x distance. So x means here very small distance. Up to small distance, this electric field is constant. Electric field is constant. See here, inside the surface, inside the thin sheet or distance from the axis, what is the electric field now? Electric field is directly proportional to x. Outside the surface, electric field is constant, means distance na d na here. See, outside the surface, what now it is constant. So constant means parallel to x axis. This is the graph for thin sheet. What is the electric field na? Inside, from axis to surface, electric field is increases. After surface, it maintains constant electric field, not for long. So some distance, small distance, it will go to long distance na, electric field is change, we know that one. See, up to small distance it maintains constant electric field. So this means constant. So here E proportional to x means electric field is directly proportional to x, means inside the surface, inside the thin sheet from axis, electric field is changes, means directly proportional. After that it will be constant. This is the electric field due to thin sheet and plane sheets, this one. So next we discuss electric field due to means uniformly charge distribution of the early model of an atom, we can discuss. See next one, an early model of an atom considered it to have a positively charged nucleus, positively nucleus of charge Ze, surrounded by uniform density of negative charge up to a radius r. The atom as whole is neutral. What is the electric field at a distance r from the nucleus? What now here see? See an early model of an atom. See here, this is the atom. This is the atom. This is the atom. See, considered it to have positively nucleus of charge Ze. So this is the nucleus. This is positive charge is filled. So this is the positive charge. So it contains positive charge. See, surrounded by uniform density of negative charge up to a radius r. See, from the center, radius r, capital R, this total is negatively charged, negative charge is distributed. Here negative charge, this one, this total is negative charge is distributed. See here, so nucleus is positive charge, this is negative charge is distributed. So that says it. See, the atom as whole is neutral. Totally, what is the atom? Not neutral. So positive charge is there, negative charge is there. So because of that, it is neutral atom. So but what is the electric field at a distance r from the nucleus, outside and inside? We want to find out. Small r distance, for example, this one. So r distance inside the atom, what is the electric field? So that we find out. Outside the point or distance from the center, what is the electric field? That we find out. For that, now here see, we can select first Gaussian surface. See, this is the Gaussian surface. So this is the Gaussian surface for early model of an atom. See, r distance, small r distance from the center, small r distance from the center. See, this is the center. From this center, this one, this is the Gaussian surface. So Gaussian surface na, what is the use of this one? Now Gaussian surface should be symmetric about charge or charge distribution. So r distance, small r distance from the center, smaller distance from the center. See here, it is the Gaussian surface, this one. See, this is the Gaussian surface, we can select. See here, Gaussian surface. In this one, electric field is same every point on the Gaussian surface, and in the same way, theta is the angle between electric field vector and area vector is same. For example, see here, in this one we can select here, It is the area vector and electric field vector. So both are same direction. For example, here you select this one, area vector and electric field vector, same direction. So this point you select now here. So it is area vector, electric field vector. Both are in same direction. This point, see area vector and electric field vector. So both are in same direction. So means theta equal to 0. Theta equal to 0. For this, in this one, due to this r distance from the center, what is the electric field? For finding electric field due to this early model of an atom, so we use Gaussian surface. Gaussian surface is here, spherical surface is the Gaussian sphere here, that is the Gaussian surface. By using this, we find out what is the Gauss law now here. Pi closed, pi closed equal to q inside by epsilon naught. This is the Gauss law. So means what is Gauss law now? Net charge, sorry, net flux through closed surface is 1 by epsilon naught times charge inside the surface. Charge inside the surface. We find out pi closed. So what is pi closed now here? See, pi closed means, see this one, area vector dA, electric field vector E. So we can write d pi. So d pi equal to what? E dA, E dot dA. So that equal to integral E dA cos theta. Here theta is what? Here electric field vector, area vector. Theta equal to 0. So we can write theta is 0. So means here integral, why we are writing now here d pi. So this is d pi. So here d pi, here d pi, here d pi. So means totally, what is the total flux through this Gaussian surface now? We can take integration here. So what we get? Pi. So pi equal to integral E dA cos theta. Pi equal to E dA cos theta. For example, see here, this is the Gaussian surface. In this Gaussian surface, what is the flux through this Gaussian surface due to its negative and positive charges? That we find out here. See, first we select Gaussian surface. In this one, some area we select. This is the area. Due to this area vector, electric field vector. Here area vector, electric field vector. Area vector, electric field vector. Theta is what? 0 here. Due to this area, what is the flux now? D pi. So here d pi, here d pi, here d pi, all d pi's added, we can take integral d pi. Integral d pi means integral E dot dA. E dot dA means E dA cos theta. So integral d pi na pi. So E dot dA na, here theta is what? 0. E dA cos 0. Cos 0 means 1. So means what we get? Integral E dA we get. So we can write E outside now here, integral dA. So integral dA means E into dA means surface area of this one, Gaussian surface. Surface area. What now here? 4 pi small r square. What is the flux through this Gaussian surface is 4 pi r, E into 4 pi r square. E into 4 pi r square. In this one, what is the Q inside the Gaussian surface? That we find out. For example, what we can do now here, see total atom, what is the flux now? Sorry, what is the charge now? Rho. Rho is the charge density in this atom. Total na what na? Rho. So means here rho equal to what? Charge per unit volume. Charge per unit volume. So means rho means here volume charge density. Volume charge density. Volume charge density means rho equal to charge by volume. That is called as volume charge density. In this one, what is the total volume now here? 4 by 3 pi r cube. 4 by 3 pi r cube. That case here, see, in this one I write here charge per unit volume. So charge equal to what here? Rho into V. Rho into V. So rho means here 4 by 3 in this one. So we want here this Gaussian surface, what is the charge? So that one na here rho means here in this one 4 by 3 pi r cube, small r cube. Yes na? 1 minute. See again here volume charge density means charge per unit volume. Volume charge density means charge per unit volume. Volume charge density means charge per unit volume. In this atom, what is the total charge now? ZE. We can write here rho equal to ZE by volume na radius is capital R. Radius is capital R. What is the volume here? 4 by 3 pi capital R cube. 4 by 3 pi capital R cube. See, in this one we want this surface. What is the charge in this surface? That only we want. So for that charge we can take it as Q dash. Q dash means what here? In this one, see, rho into V na, rho into V. So rho means rho into V. What is the volume of this one? 4 by 3 small r cube. 4 by 3 small r cube. See here, Q dash equal to rho into 4 by 3 pi small r cube. Rho means what? ZE by 4 by 3. I write here Q dash equal to ZE by 4 by 3 pi capital R cube into 4 by 3 pi small r cube. Here ZE means, here nucleus na plus ZE is there. So remaining is what? Negative na. So that's why we can write here negative. So what is the Q dash na? Here negative charge we find out, plus nucleus already we know, plus ZE. So this part we can find out. So total volume is 4 by 3 pi r cube, 4 by 3 pi capital R cube. So that only ZE, total charge is here ZE, charge is ZE by 4 by 3 pi r cube. Only this small region, so means this Gaussian surface, what is the charge now? Q dash, that is we can write rho V. Rho V means what? Here radius is small r, so means volume now 4 by 3 pi small r cube. Rho means ZE by 4 by 3 pi r capital R cube into 4 by 3 pi r cube. Here see ZE, ZE means here we only negative charge only we want. Positive charge already we know ZE this one. So this is negative now, that is minus we can write. That's why we can take here minus. See 4 by 3, 4 by 3 cancel, pi pi cancel. What is the Q dash now here? Minus ZE R cubed by capital R cube. This is the charge inside the Gaussian surface. Total charge now what we can write here? See Q inside in this one now plus ZE minus of ZE R cubed by, see I write here ZE, nucleus is ZE, negative charge is ZE by capital R cube into small r cube. ZE by capital R cubed by small r cube. See this one. See, this is the charge inside the Gaussian surface. What is the flux through Gaussian surface? E 4 pi r square. So these two equate. This equation we can take. This equation 2 we can take. What is the Q inside here? Q inside is ZE minus ZE r cube, ZE small r cube by capital R cube. So pi closed na E 4 pi r square. These two equate na here. I write here, see. So E 4 pi small r square, that equal to ZE minus ZE r cubed by capital R cube. See this one we can change this na. Here q by epsilon naught is there, 1 by epsilon naught again. See here pi closed equal to q inside by epsilon naught. Q inside is this one, pi closed is this one, epsilon naught is there. Pi closed means this value into 4 pi r square. So 1 by epsilon naught into q inside. Q inside means this one. Once this area, what is now ZE minus ZE r cubed by small r capital R cube. See here, this 4 pi, this changes this side now, E equal to 1 by 4 pi epsilon naught, or inside we can send. So ZE also we can common here. First I write here. See 1 by 4 pi epsilon naught r square ZE minus ZE small r cubed by capital R cube. See here ZE common, r square is changes to inside. What we get now here? Electric field equal to 1 by 4 pi epsilon naught. Here ZE outside we can write 1 by r square minus r cubed by r square into r cube. This r square cancel. What we get now? 1. So means what? Finally we get now electric field equal to ZE by 4 pi epsilon naught 1 by small r square minus small r by capital R cube. This is the electric field due to early model of an atom or distance from the center inside the atom. Inside the atom. What is that now? Electric field equal to ZE by 4 pi epsilon naught 1 by small r square minus r by r cube. This is the electric field due to atom or distance from the center inside the center, inside the center. See again once. So we can select first Gaussian surface at r distance from the center. So that is pi closed equal to q inside by epsilon. Pi closed, now we get e 4 pi r square. Q inside, this only part important. See here, q inside charge. What is now q inside by epsilon we want? Q inside only we want. So total charge now here, density equal to volume charge density equal to charge per unit volume. Charge is ZE, volume is 4 by 3 pi r cubed, capital R cubed. Why? Because this radius is capital R. See here, q dash. What q dash means? This part only we want, small, this Gaussian surface only. What is the charge inside Gaussian surface? That only we want here. For that we can take q dash. Q dash means rho v. So from this here, rho into v. V means here 4 by 3 r cube. Why? Because this Gaussian surface is r radius, small r radius. 4 by 3 r cube, rho. So q dash equal to rho means this one, ZE by 4 by 3 pi capital R cube into 4 by 3 pi small r cube. Here minus y we can take now here. Negative charge is here spread. This you know already ZE. That's why we can write minus here. So what is now q dash here? Minus ZE r cubed by small r cubed by capital R cube. So total charge now here, nucleus and this charge now what now we can write? ZE. Nucleus is plus ZE minus negative charge is minus ZE small r cubed by capital R cube. So what? Pi closed equal to q inside. Pi closed, this one is this one. So pi q inside now 1 by epsilon naught ZE minus ZE. Here it will be changes this side, divided, yeah, from this. See, 1 by 4 pi epsilon naught r square ZE minus ZE r cubed by r cube. Here see, ZE common, 4 pi epsilon naught common. So r square is there now here. This r square is inside, we can set 1 by r square minus r cubed by r square into capital R cubed. R square cancel, 1 is there. So means electric field equal to ZE by 4 pi epsilon naught 1 by r square minus of r by r cube. So this is the electric field due to early model of an atom from the center or distance, small r distance inside the atom, inside the atom. We want to find out outside atom also. See what is the electric field due to outside atom. Outside atom now here, see, this is the atom. See here, inside this is positive charge, outside is negative charge, this one negative charge. After nucleus is, it is a negative charge. See, from center, this is capital R, radius of the atom. So from center or distance at point P, or here this is the radius we can take, or distance, small r distance at point P, what is the electric field we find out. For that what we can do? Gaussian surface we can draw. Here see, this is the Gaussian surface. So Gaussian surface should be symmetric about charge distribution. So electric field is same at every point on the Gaussian surface. So theta is same at every point in the Gaussian surface. For example, here we can take this area. This is the area vector. Electric field vector is, why? Because here positive outwards. So electric field vector. Here this point we can take, this point. It is the area vector, electric field vector. See this point we can take now. Here see this point, area vector, electric field vector. See this point we can take now, it is area vector, it is electric field vector. See what is now? Pi closed equal to q inside by epsilon naught. This is the Gauss law. According to that we can write here. See d pi, d pi, d pi, all we can add now. See integral, so pi equal to integral E dot dA, that equal to q inside by epsilon naught. See here, pi equal to integral E dA na. So E is outside, we can write, sorry, E dot dA, E dA cos theta equal to q inside by epsilon naught. See cos theta na, here theta is 0. So we can write, so E integral dA equal to q inside by epsilon naught. So E na, so integral dA means A, so that equal to q inside by epsilon naught. A means here surface area 4 pi r square, that equal to q inside, here positive, here negative, totally atom is neutral, so that's why q inside is 0. So what na? Electric field here 0. So means due to total atom outside point tau distance from the atom. So what is the electric field? Now 0. Inside is ZE by 4 pi epsilon naught 1 by r square minus of small r by capital R cube. This is the electric field due to early model of an atom from center or distance inside the atom. This is the electric field due to plane sheet, thin sheet and early model of an atom. So thank you.